Welcome back. Remember that? That's an HB100 Doppler radar module. It transmits some microwaves and it can also receive some microwaves. And ideally you have a moving object in front of it, and at the output you get the difference in frequency from the transmitted to the received frequency. And through the Doppler formula you can calculate the speed of the object from that frequency difference, the Doppler frequency. I've already made a 3-part series about that thing, starting at the very basics, so Doppler effect, frequency mixers and so on. In part 2 we finally built a board, an amplifier board for that thing, and connected it to an Arduino and measured frequencies. And in part 3 we did some improvements to the Arduino code and the frequency measurements. A card to all parts here, links in the description. So for the basics, have a look at these 3 videos. They all have all a time index, so you can find really quickly what you are searching for. Anyway, I have 2 questions regarding these HB100 modules. First, at what frequency are they actually transmitting? And second, what's the maximum bandwidth of the frequency mixer here, and in effect, how fast can an object move and I can still measure its speed? So what do we know about the HB100 module? It transmits with 50 milliwatts, so about 12 dBm, and it comes in different frequency versions. Yeah, from 9.35 gigahertz to 10.687 gigahertz. Most likely I have a 10.525 gigahertz version, but hopefully we'll see. So, how could we measure the frequency of that thing? A straightforward approach would be to just remove the can. That wouldn't be too hard. And then with a 10 GHz bandwidth scope and a 10 GHz bandwidth probe, just, measure it. There are several things wrong with that picture. First, I don't have a 10 GHz scope with the accompanying probes. Second, even removing the can here might shift the frequency of the oscillator, let alone parasitic capacities and inductances that you introduce by, touching something inside here with a probe. So we do need another approach. And that would be to, simply take the transmitted microwave here, that's the transmit patch antenna of that thing, and receives the signal with another antenna, which I do have. It's a wideband patch antenna here, and that should be good up to 12 gigahertz or at least 10 gigahertz. And then we just need to feed that signal in our non-existent 10 gigahertz scope or into a 10 gigahertz spectrum analyzer. Talking about spectrum analyzers, maybe we are onto something here. So this is a very, very simplified schematic of a spectrum analyzer. I left out all the necessary filters, only the core elements are shown here. So basically you have your input here, and that goes into a frequency mixer. Also into the frequency mixer goes the input from a voltage controlled oscillator, and that oscillator is controlled by a sweep generator. So we are sweeping here over the frequency which we want to display the spectrum of. And as output, we don't have to handle the higher input frequencies here, but just the lower intermediate frequencies, which are the difference between the input frequencies and the VCO frequency. which is sweeping constantly. In modern spectrum analyzers, that VCO would be, of course, a digitally controlled oscillator, and you won't have a sweep generator but a microprocessor. And then the intermediate frequency would probably go into an analog to digital converter, and this is just, digital stuff. Now, the innards of an HB100 Doppler radar module look something like that, and I put a link into a teardown website into the description. We have our fixed frequency microwave oscillator, and we want to measure the frequency of that oscillator. The output of the oscillator goes, of course, to the transmit patch antenna and also into a mixer like in the spectrum analyzer. And the receive patch antenna signal is also fed into the mixer, and we get out that intermediate frequency, the Doppler frequency, which is the difference between the transmit and the receive frequency, and we measure that currently with our oscilloscope. Now, if we just had a way to, emulate that VCO or sweep generator and feed a specific frequency here into the receive patch antenna, then we could measure the frequency or the difference between the oscillator frequency and the receive frequency and therefore calculate the oscillator frequency. Well, as it happens, I do have a 40 gigahertz microwave signal generator laying around. So here's what I did. Still measuring the intermediate frequency output of the HB100 with the oscilloscope. And I kinda shaded with a metal plate the transmit patch antenna of the module. Literally shaded, obviously. So if I now move, above it, my hand, we barely get an output here, a signal. I connected my wideband patch antenna to the microwave generator, and now we will transmit a microwave signal down into the receive patch antenna. And we start with the most likely frequency of 10.525 gigahertz. And we start with 0 dB, so 1 milliwatt. And nothing happens, huh? Let's increase the transmit power here a little bit. So plus 10, we saw something, huh? If I play with the transmit power and I'm going up to 12 dBm, so 50 milliwatts. There's definitely something coming out here, but my time scale is still at 10 milliseconds. So I'm changing position here, working around the camera. Let's change that. Five microseconds. Oh, we are going into the megahertz range. And what a nice output signal, huh? Let me configure the scope for frequency measurement real quick. So I'm using here a cursor to measure the period of the signal, because normal frequency measurement doesn't work because we have this ripple on our signal. If you watch part 1, I will explain there that the output of a frequency mixer is not only the difference between the two input frequencies, but also the sum of the two input frequencies, which is in our case about 20 gigahertz far too much for my poor scope, and so we get this ripple here overlaid. Anyway, period is about-ish 140 nanoseconds, so about-ish 7 megahertz. So we are 7 megahertz off. Now, the only question is, is our HB100 7 megahertz below the 10.525 gigahertz or 7 megahertz above that? And to measure that, we simply adjust the frequency of our signal generator. So let's go to the megahertz digit here and turn that up a little bit, and the frequency gets larger. And if we turn it down, the frequency goes lower. Let me experiment a little bit with that. Okay, this is quite good here. But I think I need to reset the settings or adjust the settings on my scope. Let me fumble a little bit with that. I had to adjust the trigger level here a little bit, but now I'm moving in 100 kilohertz steps. And I'm moving my frequency here down. I'm now at 10.522 gigahertz. And I'm going down further, 10.520, and I need to adjust my scope again, just a sec. Yeah, without any filters, this is noisy as hell, but we are now down here to 10.520 gigahertz. And measuring just the period with the cursor, and of course if I put my hand here, everything goes haywire. We are down to about 2 megahertz intermediate frequency. So if we lower the output frequency of our generator, we lower the intermediate frequency. That is, we're going into the right direction. Again, remember part 1. The mixer in here just gives you the difference between the two frequencies. And you don't know which direction. Okay, so let's tune that down even further. And I have to adjust my scope again, just a sec. So we are at 10.519 gigahertz, and my intermediate frequency is about 930 kilohertz. Let's go down further. And you can see the exact relationship, but let's not go down a full megahertz, but only 500 megahertz. Let me measure again. Okay, that measures now at 420 kilohertz. So we can still go further down. Okay. 10.5182, adjusting the scope. And I measure here 9 microseconds, 110 kilohertz. So we are approaching slowly but surely, and you can see, if I take my hand out, you can see the jitter. I mean, we are approaching the jitter of that one transistor oscillator here, which I can influence quite intensely just by waving my hand nearby. So I guess we have now the frequency to 1, 2, 3, 4, 5, 6 digits. Okay, that should be enough. So that's what we measured, yeah, our signal generator frequency. We started at 10.525 gigahertz and got an intermediate frequency output of 7 megahertz. And I have to calculate what speed that Doppler frequency would relate to. Anyway, we went down and down and down, and we decreased our intermediate frequency output again and again until finally in the last step at 10.5182 gigahertz, we only got 110 kilohertz at the intermediate frequency output. And if we subtract that from our input frequency, we come to 6 digits, 10.5181 gigahertz, which is a long way from the specified 10.525 gigahertz, and could bring you probably into trouble in most countries when you actually run these things, because your Doppler motion sensor is working outside the assigned frequency band for industrial Doppler motion sensors. Let's try something else. Okay, it's the next day. Everything was switched off overnight, and now, according to the scope, I won't zoom in, but now we are 340 kilohertz off our 10.5182, yesterday's settings frequency here from the generator. So we had a little frequency shift here because it's a bit warmer today in the office and the generator was not running for that long. But to confirm if there's really a significant temperature shift in the frequency, I will hit it with some hot air. Let's see what happens. Oh, did you see that? Okay, so that's what I wanted to show you. Temperature stability basically 0. And I have a second of these HB100 modules. I will exchange them and then we'll see at which frequency that one is working. Okay, I did exactly the same as I did with that first module, which I marked now at 10.518 gigahertz. I lost some decimals because it makes no sense with these things. And I creep down from my initial 10.525 gigahertz until I come here, sorry, screensaver, until I reached here intermediate frequency output of now just 300 hertz. Good enough. We don't need any more accuracy with these HB100 radar modules made in China, or better, cloned in China. And we are at 10.4972 gigahertz, minus the 300 megahertz intermediate frequency. That leaves us with 10.4969 gigahertz. Oh, okay. That was fun. But let's have a look at the numbers again. Okay, so these were the initial measurements we took, I took yesterday, and we saw we had here overnight with a few degrees, shift in temperature here in the room, frequency shift of, let's say 200 kilohertz, which for 1-2 degrees is not too bad, but as soon as we put that thing on the board and heated it up 10-20 degrees, you saw it was all over the place with the frequency. Anyway, but our our first HB100 module came out at 10.518. Yeah, forget about the decimals. 10.518 gigahertz instead of the promised 10.525. Which is okay, at least in my country, in Germany, because there the law requires, or the law has reserved a frequency band of 100 megahertz between 10.5 gigahertz and 10.6 gigahertz for these motion detectors or Doppler radar sensors. So we're fine. The second board, which is still there somewhere, we measured with 10.4969. You see something, but I'd say within the tolerances of my measurement here, it's borderline 10.5 gigahertz, but it's still within it's still within the allocated range for motion detection sensors here. Okay. So, what should you take away from this video? Well, of course, that these HB100 modules, or to be more exact, the Chinese clones of the original HB100 Doppler radar modules, are quite crappy. But let's be honest. That's what we expected. At least that's what I expected. I mean, it's a one transistor oscillator in here, and probably in the factory, if you have a spectrum analyzer or set up like that, you can tune these things to 10.52, 10.53 gigahertz. But I don't think this is really happening, that they have that equipment there in the factory. Okay. On to more serious things. What else should you take away from this video? If you want to measure something, like the frequency of a Doppler radar module, and you have not access to the proper instruments, like a spectrum analyzer, to do it, you don't have to give up. There are always approaches to indirectly measure the quantity, so the frequency here, that you want to measure. A simple example, you want to measure a resistor somewhere in the milliohm range, but you don't have a 4-lead milliohm meter. So what do? You take a reasonable, accurate 1 amp, for example, constant current source, might be your lab power supply. By the way, my oven is working currently, or still working. And then you take your run-of-the-mill multimeter, which hopefully has a recent millivolt range. And then then with 1 amp, the millivolts displayed are directly your milliohms. So, and the same applies, of course, also to high-frequency stuff. Okay, that generator is a little bit expensive, but a 10 gigahertz signal generator plus a cheap one-transistor mixer that you can, build by your own and put a can on it, or you can buy it, is much cheaper than a 10 gigahertz scope or a 10 gigahertz spectrum analyzer. And when you are working with really high frequency stuff, mixers, to get from your 10 gigahertz down to a few hundred hertz, in this case here, mixers are always your friends. I guess that's it for today. Till next time. Bye.